So today we will be discussing some more problem on calculus. We will do some exercise problem on differentiation, limits, continuity. But before that, I would just like to add some theoretical part. In the beginning session, I have received lots of requests regarding this, that how to obtain or how to evaluate the limit from the definition. So if you do not know the definition, the analytical definition of limit, it is something like this, that we say that a limit x tends to a, this equals L, and we will say that this limit in the language of mathematical analysis in this way, that if for any epsilon greater than 0 there exists, this symbol is known as there exist, okay? Yeah, for any epsilon there exists a delta greater than 0, strictly greater than 0, such that whenever this condition hold, okay? So this is the so-called definition, or I would say so-called epsilon delta definition of limit, okay? This is what is known as epsilon delta definition. So for any epsilon, doesn't matter how much small, but not 0, strictly greater than 0, we should obtain a delta such that these two hold simultaneously. Whenever x is in this interval, then this condition should hold, okay? So in this connection, I just want to add one more thing here, that open interval and closed interval. Open interval and closed interval, okay? So what is an open interval and what is a closed interval? Well, I will not go into the detailed mathematical analysis right now. Maybe it require one more session for that to describe this vividly, okay? So therefore, I will stick to the concept in one dimension, okay? I will not go higher dimension in this session at least. So in one dimension, what is an open interval and what is a closed interval? Well, any interval, say like this, where we do not take the boundary points, this A and B are the boundary points, say this. So any interval like this where we do not take the boundary, we mention this interval in the definition of set likewise in this way, x such that A strictly less than x strictly less than B. So this is the set in which these two boundary points A and B are not included, right? See, from here the expression, it is strict. It is strictly less than, strictly less than. So in this set A and B are not included. These are excluded. So this type of interval we called as open interval, okay? And when we say it is a closed interval, so if we include the boundary points, then we will say it as closed interval. Yeah? And we denote this in this symbol, okay? This is first bracket and this is third bracket basically, okay? So for the time being, this is sufficient for at least 12th grade of mathematics. This much knowledge is sufficient. What is open set, or you can say open set, you can say closed set. Whenever the boundary points are included, we call this as a closed interval, and whenever the boundary points are excluded, we call this as open interval, okay? Later on, you maybe get to know about limit point, interior point. It is a more details analysis. So we will discuss this in another class, which is much more advanced mathematics, not required for class 12 at least, maybe undergraduate, graduate, or master's level courses. Okay. So why I am saying this? It is because, see, whenever you will encounter the definition of limit, theoretical definition, this epsilon delta type of definition, there are lots of variations of these definitions. Okay. So you will never ever encounter this closedness. Okay. Yes, you will always encounter this strictness. There should not be any equal symbol you will find. See, any definition, you go anywhere, even in the higher dimension, whenever we are evaluating the limit in higher dimension, the definition you will always see in the form of open interval set. So see, can you find the similarities between this, see? Everywhere you will find a strictness, that is an open interval kind of thing, okay? So the definitions of limit, the definitions of continuity, the definition of differentiability, or any definition which is the fundamental something defining some concept, you will encounter this open interval kind of thing, okay? Therefore, studying the open interval is very important. So here, if we see now from this definition, how can we prove the limit? If some problem is given to you, then how can you prove that this limit exists or not from the definition? Sometimes it has been asked in the questions that prove from the definition that this limit exists. Say for example, let's go to another page. Say you have given to this problem that prove that, I am using some different color, it will be easier. Prove that limit x tends to 3, 2x equals 6. This question is given to you. Now you will be asked. Now if you go by simple mathematical way, it is very easy to prove, right? But in the question it has been given that you have to prove this using the definition of epsilon delta. From the basic definition, prove this equals this. Then how you will do this? So what was our definition? In that case, our fx equals 2x, right? So we have to find, what we have to do basically, for any epsilon greater than 0, no matter how small, we have to find a delta greater than 0 such that fx minus 6 strictly less than epsilon whenever 0 strictly less than x minus, here our a is 3, right? X minus 3 less than delta. We have to prove this actually. We have to prove this, that in this case whether it is happening or not in this problem. Now I will do this. So if you have any doubt, let me know. But I don't think you would have any doubt because it is very simple. Once you do 2-3 exercise, you can grasp the knowledge that what is going on in the background. Now let's see what is fx in this case. We have fx in this case 2x, right? So 2x minus 6 less than epsilon. So any problem, if it is given to you, you start from this. This would be the first step, okay? You start from here, that 2x minus 6 less than epsilon, or fx minus L. What is your fx? What is your L? Put that into the modulus and then in the right hand side, strictly less than epsilon, write it. Now see, the next step, what we will do, since this is a mod, and 2 is a positive number, we can put 2 outside of this mod. And from here, what we obtain? we obtain x minus 3 less than epsilon by 2. Now, what we obtain as delta, we can say from here that we will choose if delta equals epsilon by 2, or you can write choose delta equals epsilon by 2. What we obtain? That if delta equals epsilon by 2, then it is following, because from here we arrive this step, right? Therefore, we can say that 2x minus 6 less than epsilon whenever 0 equals delta equals epsilon by 2. Yeah. Now, another interesting question here, that why we write here on the left hand side, why we write this as 0? Because this is a modulus, right? This is a modulus, right? So modulus is definitely positive. So why we are writing this, that 0 strictly less than this kind of thing? Because we do not want x to be equal 3, okay? It is true that modulus is always positive, but modulus is, you cannot say modulus is strictly positive. You can say modulus is non-negative. If you take the very precise versions in mathematical terminology, it is non-negative kind of thing. That means it can be 0. Modulus can be 0. Mod x, you cannot say this. You can say this. Yes? But if we are restricting that, if it is strictly positive, it means that we are taking x should not be equal to 0. Whenever we are writing this, it means that x is not equal to 0. It means x, mod of x is strictly positive. So the meaning is same here. Whenever we are mentioning this in the definitions of limit, it means that we don't want x to be 3. We are excluding this value from the interval. So for that reason, we write this. But even though this is true, even if x equals 3, but from the definitions of limit, we will respect the definition of limit. We will not take the value of the limiting. The limiting value we will not take. So for that reason, we put the expression in this form. Okay. So now I hope that how to solve this kind of problem, you have get some idea, right? I will do some more problem. So don't worry. I will share some more example. Let's say you have given from the basic definition, prove this problem number 2. Prove that limit x tends to 5. You have to prove that 10x plus 2 equals 52. So you have to prove this, okay? Then how you can prove this? Very simple. We will follow the same definition. First step, what we will do? 10x plus 2 minus 52 less than epsilon we will do, okay? This implies 10x minus 50 less than epsilon. From here, yes? Same method, we will choose this equal delta, and hence we obtain, therefore it is true, right? Yeah. Now let's try some different problem. Let's take this one. Limit x tends to 0 plus root over of x equals 0. How you can prove this? Try it by yourself. Pause the video, try it by yourself, and then follow the method I am doing here. So we will, the first step, what is our first step? Fx minus L less than epsilon. Yes. What is our fx? Root x. What is our L? 0. Yeah. root over of x implies less than epsilon implies taking square root to both sides. Very simple. From here we obtain this equal delta. We will just write. Therefore, yes, pretty simple, right? So let's take another problem. I hope you are grasping the idea, okay? How to solve this kind of problem. It's very simple. There is nothing difficult here. How you can prove this? You have to prove this from the basic definition. First step, x square minus 16 less than epsilon, okay? We can write this in this way, yes. Now, what we need? We need this kind of thing, right? We need something, some sort of this kind of thing. But from here, did you think that we can directly observe this kind of thing where delta is some real number, okay? Yes, we can do this. See, I'm just doing this for a rough. We can write this in this way. X minus 4 by modulus of x plus 4, okay? But this cannot be a delta, isn't it so? Because this is not a real number. Here x is a variable. We need to make this expression as some real number, or we need to find some bound so that we can get some control in order to get some real number, right? So this is not a real number, so you cannot do this operation, yes? So here we need some tricks, and the trick is this. It is nothing so important trick. Anybody can do this. Once you get to know this, you can easily solve this. There is nothing so special tricks here, okay? So what we are going to do here, we will follow in this way. Let delta less than equal 1. Now you can ask that why we are taking delta less than equal 1. Well, first of all, you can take any value of delta, okay? 1, 2, 3, 4, 5, 6, 7. But if you are taking 5, then if the result is true for 5, then it is automatically true for 1, right? If the result is true for higher range, then it is automatically true for lower range. Yes? So for that reason, I am taking delta less than equal 1. Yes? So any number which is less than 1, say 0.5, 0.2, in that case also, whatever I am going to prove now will remain same. Yes? Because I have taken less than equal. And if you are taking something greater than 1, say if you are taking greater than 5, then also these results will be true. Yes? As I mentioned, if it is true for higher range, then definitely it will be true for lower range. Correct? So what we are going to do now, we will substitute this expression here. Okay. We can write this in this way. X plus 4 minus 8. Because this one is strict, so that's why it is strictly less than 1. Now, what we are going to do, we will apply this inequality. This is a well-known formula from inequality, right? Modulus of A minus modulus of B strictly less than equal modulus of A minus B. This is B, okay? So if we are assuming this as A and this as B, then we can write x plus 4 minus 8 less than equal x plus 4 minus 8 less than 1. Simplifying, we obtain x plus 4 minus 8 less than 1. That is, we can say x plus 4 less than 1 plus 8 equal 9. So as I mentioned earlier, that we need some bound for this expression, right? So we obtain a bound for this expression provided delta is less than equal 1. So if delta is strictly less than equal 1, then we have this bound for this expression x plus 4. So now what we have to do is first see that what we need. We need this expression, right? Let's mention this as equation 1. Okay. Basically what we need a delta such that whenever x satisfy this condition, we should have this. Yes, whenever this condition is satisfying, this should hold automatically. This we need to prove actually. And in order to prove that, what we did, this was our first step. There wasn't any change here. But what we did next, we choose a delta which is less than equal 1. We just choose it. We didn't say anything about that. We just choose it, and then we obtain an expression which is bounding this expression. Okay. So if delta less than equal 1, then we have x plus 4 modulus less than 9. So from in equation number 2, we have x minus 4 less than delta. We multiplied both sides with x plus 4. Now, if delta less than equal 1, then what will happen? Less than equal 1, then we can write this expression. Nine delta, right? From here, correct? So here we obtain that x square minus 16 less than 9 delta. So can you think what would be our final step? We need one more step. The problem is almost finished. It is 95% finished now. We need one more step here actually. And that step is, in order to satisfy equation 1, that is this one, we need this thing to be less than epsilon, right? Correct? If this 9 delta is strictly less than epsilon, then we are arriving this conclusion. We are arriving this inequation, right? Let me now summarize what we did. We choose delta less than equal 1, and then we arrive here that 9 delta should be less than epsilon. Only then inequation 1 is getting satisfied, right? So what is the technique here is basically what we have to do, since choosing of delta is in our hand. So if we now choose delta equals minimum of 1 and epsilon by 9, then delta is satisfying both of this condition, right? If we choose delta minimum value of 1 and epsilon by 9, then both this condition is getting satisfied, correct? Therefore, from now onwards, we can say that whenever this x lies in this range, we have x square minus 16 less than epsilon, correct? Because since delta is minimum of both of this real value, therefore this means we have this, and we also have this, correct? And we have this, it means we also have this, correct? Yes? If you have any doubt, let me know, okay? Let us now discuss about composite function theorem for continuity, okay? So basically, what is this? That let's say if x is continuous at say x equal a, okay, and gx is another function which is also continuous at x equals a, then composite function, you know what is composite function, right? We have learned this in the function chapter. Then this composite function theorem is saying that f of gx and g of fx both are continuous at x equal a. Okay, so this is the composite function theorem, and it has lots of application. Okay, before going to the application, let me just say you one more thing, that you can even extend this theorem in the sense that because a is any arbitrary point in the real number, right? So if you know that fx is continuous throughout R, okay, or any subset of R, and but I will assume on R so that we can make this more universal. Okay, say fx is continuous on R, and gx is also continuous on R. Then g of fx and f of gx both are continuous on R. Okay, you can prove this actually. Okay, so with the help of this we can solve lots of problems. Okay, let me just give you some example so that you can understand. So let's say you have given that if this is continuous at say x equals c. Okay, either you have been asked such a question or you have given to prove or disprove. So let's say, so the thing is this, that you have to prove or you have to say whether it is true or false, that what about root of fx, is it continuous or discontinuous? Now if you think this definition or if you go by this logically, then it might be difficult to solve. Okay, but what we are going to do here, we are going to apply composite function theorem here. Okay, we will assume another function, say gx equal root of x. Now we know that gx is continuous on whole R plus, right? That is set of all non-negative real numbers. Yes. So if c is positive, if c is greater than equal 0, then we will use composite function theorem to show that this is continuous on whole R plus. Yes, or this is continuous on C. Yes, because fx is continuous at C. See, follow this definition, fx is continuous at C, and since we have assumed that C is a non-negative real number, so gx is also continuous at C. Therefore f of gx is continuous at x equals c. Yes. Similarly, you can also show that, let's say fx is continuous at x equals c. Okay, now you have to determine that what about modulus of fx, is it continuous or what? Well, we will follow the same technique. You can choose gx equals modulus of x, right? And you know gx is continuous on whole R. Yes, and c is given any arbitrary real number. Yes, so g of fx we obtain modulus of fx. So this is continuous at x equals c. Yes, because g is continuous at x equals c and f is continuous at x equals c. Therefore, by the help of composite function theorem, we have g of x is continuous at x equal c. Yes. Okay, so these are some simple example. We will do much more complex example right now, but what is the underlying idea is with the help of this composite function theorem, you can solve different problem directly within 2 lines. Yes. So we are now going to do some composite function problem. Okay, given a function fx which is defined in this way and gx is a composite function f of fx, we have to find the discontinuities of this function g. Yes, so what we are going to do first, we will first define the function and after that we will investigate its discontinuity. Yeah, so f of fx, You just have to replace x by fx. Yes. Correct? This is pretty simple, right? We just replace x with fx. Yes. So when fx is inside this interval from 0 to 2, we have 1 plus fx, and when fx is inside this interval from 2 to 3, where 2 open and 3 closed, then the value is this. So now with the help of this equation, we need to interchange this accordingly. So when fx is from 0 to 2, so when fx is from 0 to 2, we have to determine that first. Well, here observe that we have when x, it is just some sort of calculation, nothing more than that. You just have to do the calculation little bit. When x varies from 0 to 2, we have fx is 1 plus x, right? Therefore 1 plus x varies from 1 to 3, right? Correct? Similarly, when x varies from 2 to 3, fx, that is 3 minus x, whenever you are multiplying inequality with a negative symbol, inequality gets changed. Yes? So this is 3 minus x. So basically this is fx. Yes? When x belongs to this interval, then fx varying from 0 to 1, and when x belongs to this interval, then fx varying from 1 to 3. But we are interested in 0 to 2. What is happening when fx is varying from 0 to 2? What values of x fx is varying from 0 to 2? Okay. Well, definitely this interval will come, right? Because from 2 to 3, fx is varying from 0 to 1. Correct? So we will write this here. I am putting some large bracket because we have lot of subsection here. Okay. So the first subsection is when x varying from 2 to 3, fx is varying from 0 to 1. Fx is, yes, fx is running from 0 to 1, correct? So we will write here 2 strictly less than x less than equal 3. We have this definition. Yes, because whenever x is here, I hope you understand this, right? Whenever this is happening, this is automatically happening, right? Correct? From here and from here. I do not want to make this thing dirty so that it will be easier to understand. So we get one interval from 2 to 3. We have to find another one because we need fx to vary from 0 to 2 basically, correct? But here it is from 1, but we need more. So this more thing come from here. So 1 to 3 from when x 0 to 2. Now see that if here it is 1, so what I am saying is you take this and rewrite here once again. If it is something like this, then we can say this thing, right? Correct? So when x varying from 0 to 1, then fx varying from 1 to 2, correct? So we obtain the later missing point. So when x varying from 0 to 1, we have fx varying from 1 to 2. Earlier we have fx varying from 0 to 1. This one is from 0 to 1, right? Fx, yes, but from here we get 1 to 2 fx. Did you understand what I am saying? From here to here, when x belongs to, I am repeating it once again so that you can understand, because later on I will do it rapidly, I will not explain. So understand this once again, I am repeating it, okay? So see, I will start from the beginning. See, when x is from 2 to 3, when x is from 2 to 3, what is happening? When x is from 2 to 3, our definition of fx is 3 minus x, right? And from here we obtain that fx 3 minus x, that is fx varying from 0 to 1. When x belongs to 2 to 3 in this interval, fx varying from 0 to 1. So 0 to 1. So 0 to 1, when x is from 2 to 3, fx is 0 to 1, correct? So this thing cover here. Now, because this whole basically 0 to 1, right? Correct? Sorry, equality will come here. This whole thing is basically 0 to 1, but we need 1 to 2. And inside this whole interval, the definition is 1 plus fx, right? So we have 0 to 1, but we need up to 2. So for that, what we did? We took this definition. Back to this definition, we have 0, when x is varying from 0 to 2, we have fx is from 1 to 3. But we need fx from up to 2, not to 3. So for that, what we did, we make it 1 minus from here. Okay, so we obtain from here, we obtain that when x is varying from 0 to 1, we have fx from 1 to 2. So fx, when fx is 1 to 2, when we have x lies from here, right? From 0 to 1. Correct? So, what we finally obtain? We obtain one interval of x, that is 2 to 3, and another interval of x, that is 0 to 1. So, let me just now erase this. So, another interval we obtain 0 to 1. Correct? So, what we finally obtain? We obtain fx equals 1 plus fx when x varying from 2 to 3, and also when x varying from 0 to 1. Okay, so when x varying from 2 to 3 and when x varying from 0 to 1, we have fx is from 0 to 2. So the definition will match 1 plus fx. Now what about 3 minus fx? When fx varying from 2 to 3, can you do this by yourself? Try it. When fx varying from 2 to 3. Now check here. We have 1 to 3 in this case, but we need 2 to 3. So we'll use some different color. You do it by yourself, okay? Try it. Don't follow my video continuously. You need to try by yourself. Only then you can learn, okay? You try it, think. After that, pause the video, and after that, come and check whether you are right or wrong, and correct it by yourself if you are wrong, okay? So, but we need here from 2 to 3. But we have here 1 to 3. fx is from 1 to 3, but we need 2. We need 2 here. So, how can we get 2 here? That is the question, that how can we get 2 here? So, we'll follow the same strategy. We have fx equal 2 when x equal 1, right? So, we will start in this case from 1. Less than equal x, less than equal 2. Instead of starting from 0, we will start from 1 because we need 2 in the left hand side. So 1 plus 1 less than equal 1 plus x less than equal 1 plus 2. So it is 2 less than, this is implies that 2 less than equal fx less than equal 3. So we have fx from 2 to 3 when x varying from 1 to 2, right? So there is only one option here. When x varying from 1 to 2. So when x varying from 1 to 2, only then fx is 2 to 3, correct? But we have strict here, fx is strictly greater than 2. So we need strictly greater. So we should not take the equality sign here, okay? So the equality sign will not come. So when 1 strict less than x less than equal to 2, we have 3 minus fx. Did you understand what I did here? Should I explain again? If I need to explain again, if you have found any difficulties understanding this part, let me know in the comment section, okay? Because I have already repeated this part, that what I am doing basically. So, but if you still have any doubt, let me know in the comment section, okay? This is basically some sort of calculation, that's all. There is nothing special tricks here, okay? So I will now write the definition in a neat and clean manner. So we have 1 plus fx when x varying from 2 to 3. 1 plus fx when, okay, we have 1, at that time the definition is 3 minus fx, and again when x 2 to 3, at that time the definition is again 1 plus fx, correct? Yes? I hope this part is clear, right? I just manually rearrange this, that's all. Okay, now see, when x varying from 0 to 1, the definition of fx is 1 plus x. So it is 1 plus x, 0 x, yeah. Now when x is from 1 to 2, the definition is again 1 plus x. Correct? Because this is 1, x1 to 2. Now when x is from 2 to 3, the definition is 3 minus x. 1 plus 3 minus x. 2. Yes? Simplify it. What do you obtain? 1 plus x. 2 plus x. Let me use different color. 1 plus x, that is 2 plus x. When in this interval 3 minus, it is 2 minus x. When 1 plus 3 minus x, it is 4 minus x, right? 4 minus x. Yes, 4 minus x when x varying from 2 to 3. 2 minus x when x varying from 1 to 2. And 2 plus x when x varying from 0 to 1. This is closed interval, this is semi-open closed interval, and this one is also semi-open closed interval. Now, this is our gx actually. Yes, this is our gx or f of fx. So now we have to determine the discontinuity. Now it's a cakewalk. Yes, there is nothing difficulties here. We have to evaluate the discontinuity point, and we know, we have seen in our last session that discontinuity in this case we have to check at the breaking points, because these are all polynomial function. Yes, 2 plus x is a polynomial function, so it is continuous everywhere. 2 minus x is a polynomial function, so it is continuous throughout this interval. 4 minus x is polynomial function, so it is also continuous throughout this interval. So the question of discontinuity will occurs only at the breaking points, that is 1, 2, correct? So you have to check at this breaking point, that what is happening at this breaking point, that's all. After that, finish. So let's do it here. Let's finish it here. So what is happening at 1? So for that, what we are going to do, we will just check the left hand limit and right hand limit, okay? So limit x tends to 1 minus, we have to just check the left hand limit and the right hand limit. So what we are obtaining from here? Limit x tends to 1 minus. So f of fx, what is the value of f of fx? When x is 1 minus, that is here, right? 2 plus x, correct? Because 1 minus means less than 1. And this is 1 plus, that is greater than 1. It is 2 minus x. Value is 2 minus x. Yes, this one. So what is the value? Here the value is 3 and here the value is 2 minus 1, 1. So this is not equal. Therefore, 1 is a point of discontinuity, correct? Let me use some different color. Orange. So 1 is a point of discontinuity. Okay. Similarly, let's check at 2. What is happening at 2? What is the left hand limit here? It is 2 minus 2. And what is the right hand limit? It is 4 minus 2. Yes. It is 2 and it is 0. Is not equal. Therefore, 2 is also a point of discontinuity. Therefore, f of fx has discontinuity at these 2 points, 1 and 2. Correct? It has 2 discontinuity, both at the breaking point. See, 1 and 2. Okay. Given a function which is in this form. In the advanced mathematics, when you will learn, you will notice that this type of function has special name. Just for your information, I am letting you know this. This is called as a linear transformation. Okay, this is very important function. You learn this in linear algebra course, that function in this type, which you can write in this way: fx plus y equal fx plus fy, and f of ax equals a of fx. For any a belongs to R. This type of function is called linear transformation. Anyway, so let's now get back to the problem. Given that fx plus y, so it is some sort of linear transformation, and if the function fx is continuous at x equals 0, then fx is continuous at all x. Actually, it is true that a linear transformation is a continuous function, but here you have to prove this. Okay, given that it is continuous at x equals 0. So what we are going to do now, we will take, since it is given to show us that it is continuous at all x, that is, we have to show that it is continuous over whole R, right? You have to show that it is continuous over whole R. So what we are going to do, we will take any arbitrary point. Let alpha be any points in R. We don't know which point. If we can prove this in any arbitrary point, then it means it is true in the whole R, right? Because we are not imposing any condition on this point. It is any arbitrary point. So we will show that f is continuous at alpha. We will show. So the underlying idea is very simple. We need to follow the definition of limit, left hand limit, right hand limit, and equals f alpha. Limit x tends to alpha minus, basically we have to prove this, x tends to alpha plus equals f alpha. Okay, but now you are thinking that we don't know the value of f alpha, then how we can do? Nothing to worry. We do not even need the value of f alpha actually. So let's start with the left hand limit first. Limit x tends to alpha minus fx. This we can write in this way. Limit h tends to 0 minus. H tends to 0 minus. That is, h is converging to 0 negatively from the negative hand side. That is, h is negative. Okay. If alpha plus h. Yes, we can write this from the definition of limit. This equals limit h tends to 0 minus f alpha plus fh. Correct? From the definition. This equals, since alpha, it is h free now, so we can put this outside of the limit, plus limit h tends to 0 minus f of h. Correct? But since given f is continuous at x equals 0, therefore this is left hand limit for 0, and this we can write as f of 0, because f is continuous at 0. Therefore left hand limit of 0, right hand limit at 0, and f0 all are equal. Correct? Now we will investigate the right hand limit. Right hand limit x tends to alpha plus fx. This we can write limit h tends to 0 plus, correct, f of alpha plus h. Here we are interested in the right hand side of the 0 because we are evaluating right hand limit, correct? Similar procedure, f alpha plus limit h tends to 0 plus f of h. Yes, this is f alpha. Since similar argument, f0. Correct? So see what we obtain. We obtain left hand limit equals f alpha plus 0, right hand limit equals f alpha plus f0, but left hand limit and right hand limit equal. So it shows that limit x tends to alpha exist. We have limit x tends to alpha minus fx equals limit x tends to alpha plus fx. So this means that the limit x tends to alpha exists, implies limit x tends to alpha, this exists, that's all. Nothing more than that. But we have to prove the continuity. That is, we have to prove this one, that all these three expressions are equal. We have proved only these two are equal. We also have to prove this one. So for that, what we have to do? We have to just prove that f0 equals 0. Yes, but this will come trivially from the definition actually. See, if x equals 0 and y equals 0, since this is true for any x and y, so we can write this f0 plus f0, correct? From here, 0 plus 0 equals 0, and this is 2f0. Simplifying, we obtain f0 equals 0. So f0 equal to 0. Therefore, we are done. We are finished now. F alpha plus f0 equal f alpha. Correct? Therefore, do I have to say anything else now? This is f alpha. This is also f alpha. And finally, we obtain this expression. Yes? We will now start doing some problem on differentiability. Maybe in this session, I will just start it, and in the next few sessions, we will go some more details descriptions on differentiation. Okay? It's a very important concept. Lots of things are involved here. So starting with, what is the definition of differentiation? So we have seen this in our last session, that when we are going to say a function is differentiable, okay? Let's say f is any function, and we will say that it is differentiable at x equal a if this limiting value exists. So throughout the calculus, you will find everything about limit only, okay? Left hand limit and right hand limit should exist, okay? And they should be equal. So whenever these two expression exists individually and equal, only then we will say that f is differentiable at x equals a, okay? So this is the basic definition. So now you can prove that, let's say if f is any function, say fx equal a trigonometric function sin x, you can show that sin x is differentiable throughout R, or cosine x, you can show that cosine x is differentiable throughout R. So you try this in your home, or you can also take some examples. Look, I will not do this here, but in this connection, I will give you some hint that how to obtain the differentiation and what is its application, which is more important. So diving to that part, let's say you have given a curve fx equals square root of x. So as I mentioned, differentiation is basically a tangent of a curve. What is the geometric significance of differentiation? Say you have a curve here, any arbitrary curve, okay? So differentiation mean at this point, so let's say this is x equal a point. So differentiation at x equal a of any curve means the slope of the tangent, okay? The slope of this tangent. So fx equal to square root of x, and you have to determine the slope of this curve at x equals 2, say. Then how we are going to do? We will just evaluate the differentiation at x equal to 2. Now I think you know this, that f dash x, you know the formula of differentiation when fx equal xn, right? The formula is nx n minus 1, right? Provided n is not equal 1. So since here n equals half, x equal, what does it mean? It is x to the power half, right? So if I differentiate this, the formula is half x half minus 1. Yes? So here we obtain 1 by. So the slope of the tangent at x equal to given by f dash 2, this is half square root 2. Similarly, you can also evaluate the slope of the tangent at x equal 3, x equal 4. Remember one thing, that at x equals 0, it is not possible, because in that case, the denominator will be 0. Yes? So f dash will be infinite. So differentiation does not exist. Apart from that, differentiation can also be helpful when you are calculating velocity in physics. Okay. So let's say you have given a particle is moving with this formula is given. The position function of the particle is given by this formula. Okay, so let's say s equals 1 plus any arbitrary expression, say 5t plus 4t square. Okay, this is the st expression. S is displacement, t is time. So you can say position time expression or function given. So you have to find the instantaneous velocity at t equals 2. Then what you are going to do? ds dt. Yes. Differentiation of constant function is 0. Differentiation of t is 1 and 4 times 2t. Yes. From this formula, we know t to the power n, its differentiation is, what is? Nt, n minus 1. So we just evaluate this formula here. 5 plus 8t, correct? So instantaneous velocity at t equals to 5 plus 16 equals 21. So you often encounter this type of problem in dynamics, in physics, in kinematics. Okay. So in this way you can solve this. Let us now solve some numerical problems on differentiation, and it might be a little bit of advanced, but you can still see that what we are doing, so you can get some idea. Okay. But if you found this difficult, then just let me know in the comment section. Yeah. So given a function f differentiable from R to R at C belongs to R and fc equals 0, we have gx equal modulus of fx. Then at x equals c, we have to check that which one of this one is true. Yes. So if g is not differentiable, g is differentiable, it's not differentiable, not differentiable. Okay, so let's start with the checking of differentiability part. Yes, we know how to check. We have to check the left hand limit and the right hand limit. Are they exist? And okay, if they exist, then are they equal? Both things you have to check, existence and equality. So I will do this equally. So we have gx equal modulus of fx. So this equals x tends to c minus mod of fx, and gc, that is modulus of fc. fc is given 0. So this is 0. X minus c. Yeah. And what about this one? Limit x tends to c plus gx modulus of fx, gc modulus of fc 0, x minus c. Simplifying, we obtain x tends to c minus modulus of fx upon x minus c, and here we obtain x tends to c plus modulus of fx upon x minus c. Yes. Now observe that we can write this one in this way: minus limit x tends to c minus. Observe carefully and let me know if you have any doubt. Yes, because x tends to c minus, because it means x is less than c. Therefore, x minus c is negative. So we can write this in this way: minus of modulus of x minus c, right? This one Here x minus c is positive, so there is no need to take any symbol outside. It will be automatically in this way. Now since limit can go inside the modulus, we can write this in this way. Yeah. Similarly here also, we can write this in this way. Correct? I hope there isn't any doubt yet. So now what is this? You can say it is basically this thing, right? Yes, this is f dash c because f is differentiable. So this is an fc is 0. So this is f dash c inside, but we have a modulus, and this one is modulus f dash c, right? Now you can see clearly that this differentiation exists only if these two are equal. And when these two things can be equal, if this is not equal 0, these things cannot be equal, right? Because this is negative and this is positive. So in order to exist the differentiability, we need f dash c to be 0, right? F dash c should be 0. Therefore, g x equals modulus of fx is differentiable if f dash c equals 0. Therefore, D is the correct choice. Okay, so next problem we have, if f is differentiable and f2 equals 6, then we have to evaluate the limit. Now, in order to evaluate this limit, we need to apply L'Hopital rule, okay? If you do not know L'Hopital rule, it is something like this. This limit in 0 by 0 form or in infinity by infinity form, then this equals this. I will make you understand this with an example, but before that let me just write down the formula. You can differentiate and put it into the limit form. If it is again in the 0 by 0 form, then again you will differentiate until and unless you obtain a finite thing or a definite thing, okay? So let me now give some example. Let's say, I will give you some very simple example. Let's say fx equal sin x and gx equal x, okay? Therefore, we will now want to evaluate this limit. X tends to 0, sin x upon x. Now see, it is in 0 by 0 form, right? Because x, when x tends to 0, sin x equals 0. When x tends to 0, x is also equals 0. So it is in 0 by 0 form. So here we can apply L'Hopital rule, and after applying we obtain differentiation of sin x, cosine x, and differentiation of x 1. Now this is not in 0 by 0 form because in the denominator we have 1 and x tends to 0, cosine x equal 1. Therefore the value of this limit is this, okay? Let me give one more example. Let's take fx equal x square plus sin x and gx. I'm just choosing some simple example from my mind, that's all. And gx equal x, okay? So if we now evaluate this limit, x tends to 0, x square plus sin x by x. Now it is in 0 by 0 form because x tends to 0, numerator is 0, 0 plus sin 0, 0, and x tends to 0, denominator is also 0. So we will apply L'Hopital rule, x tends to 0, 2x plus cosine x, denominator is 1, it is not in 0 by 0 form, 2 times 0 plus cosine 0, 1, so the answer is 1. So this is the L'Hopital rule and we are going to apply this here, okay? So let me just erase this. We have to evaluate this expression. So observe that it is in 0 by 0 form. We have the limit x tends to 0, 6 fx 2t dt by x minus 2. Denominator is 0 because x tends to 0. And numerator, if x tends to 0, we have f2 equals 6, right? What is happening? Check the numerator. 6 fx 2t dt. Now, if x tends to 0, then fx tends to f2, yes? And f2 equals 6. So, basically it is 0, correct? So, it is in 0 by 0 form, so we can apply L'Hopital rule here, okay? So, applying L'Hopital rule, x tends to 2. Let's assume this as fx by x minus 2. What is fx? We assume fx equals this, the numerator one. So, fx by x minus 2, applying L'Hopital rule, we have f dash x, sorry, our limit will come in the left hand side. Applying L'Hopital rule, we have f dash x by x minus 2, this one. Now it is no more in the form of 0 by 0, yes, because denominator is 1. So we can now safely evaluate the limit. So we have to evaluate this one, f dash x. What is f dash x? Now this is the fundamental theorem of integral calculus that we will learn this later, that f dash x, this is basically 2fx, okay? We will learn this later actually. Actually the formula is something like this, that if, I'm also writing the formula here, that if fx equal a to, let's say phi x, and we have another function here, say ft dt, okay, then f dash x is f of phi x times phi dash x, okay? This is a formula. So we are just going to apply this formula here. So it is 2fx times f dash x, okay? So limit x tends to 2, f dash x will be 2 of fx from this formula. 2 of fx, since we have ft is 2t, ft is 2t, so we will just replace the value of t by fx, phi x here, so it is fx, so it is 2fx times f dash of x, okay? Now 2 of fx, it is 2 of f2 times f dash 2, yes? But we know our f2 is given as 6, therefore it is 12 f dash 2, yeah? So the answer is A, okay? I hope this part is clear, right? Only the unknown thing is this one, but I have also given you the formula. So I hope you have understood this. If you are having any doubts, let me know, yes? Given f2 equals 4 and f dash 2 equals 4, then we have to evaluate this limit. So let's just substitute the value first. We have f2 equals 4, so it is 4x minus 2fx. This one is simple, you can try it by yourself, okay? And we can take 2 common outside, it is 2x minus fx, right? This is x minus 2. 2 x tends to 2. We have, simplifying, we obtain this expression, yes? Now see, we know f2 and we also know f dash 2. So at any cost, we need to transform this into f dash 2, yes? So what is basically f dash 2? F dash 2 is basically this thing, right? Limit x tends to 2, fx minus f2 upon x minus 2, right? And we know f2 equals 4, so fx minus 4, we need some kind of this thing. So this 2x we can write in this way. So it is just some sort of tricks. There is nothing so difficult here. We can write this in this way, x minus 2 plus 2, right? This is just a simple tricks I am applying. I am not doing anything special. Everybody can do this. Even you can also think and do this. There is nothing so difficult here. All you need to practice, that's all. So this we have 2x minus 2 plus 4 minus fx, yes, x minus 2. Now if we separate them, we have 2x minus 2 upon x minus 2 plus limit x tends to 2, 4 minus fx upon x minus 2. Now it is clear from here, it is 2 and this one is minus of f dash 2, right? Yes. So finally we obtain our answer. It is 2 f dash 2, that is 4 minus 2 f dash 2. Yes. And we know f dash 2 equals 4. So if we substitute this, 4 minus 2 times 4, it is minus of 4. So the answer is C. Yes, minus of 4. Okay. I hope you have understood this, right? The only tricks we apply here, this one. We just expand x as x minus 2 plus 2. That's all. And after that, we just do some simple calculation. There is nothing. It is simple. You can try this. It's a simple tricks. Even a class 5 student can also do this. It is nothing difficult. Yes? You know what? You can also solve this problem with another technique. Can you tell which one? Just now we have did this. Exactly. It is L'Hopital rule. With the help of L'Hopital rule, it can be done in a single step or almost 2-3 steps. Okay? So let's try that one also. So why I am saying that? Observe that this is also in 0 by 0 form. See? Let me write down the limit. X tends to 2, x f2 minus 2fx upon x minus 2. Now see that it is in 0 by 0 form. If x equal to, we have 2f2 minus 2f2 by 2 minus 2. It is in 0 by 0 form, right? So we can apply L'Hopital rule here. So applying L'Hopital rule, what we will obtain? We have to differentiate the upper one and we have to differentiate the lower one, numerator and denominator separately. So we have differentiating, I always forget this, write down the limit. Differentiating, we have f2 minus 2 f dash x and denominator we have 1. Yes, correct. See, 3 steps. As I said, f2 minus 2 f dash 2, and we know f2 is 4, f dash 2 is also 4, answer is minus 4. Yay! Okay, so applying the same technique, we are going to solve another problem. First, you have to check that whether you can apply L'Hopital rule here or not. So for that we need 0 by 0 form or infinity by infinity form. Till now we haven't encountered this, but maybe in future we will encounter this one also. So first check that what is in the numerator. We have f1 gx minus fx g1 minus f1 plus g1, right? Now if x tends to 1, we have f1, let me write x tends to 1, f1 g1 minus f1 g1 minus f1 plus g1. Now f1 equals g1, so this will get cancelled out, and f1 g1, this will also get cancelled out. So in the numerator we have 0, and in the denominator do we have 0? Yes, we also have the 0 because g1 equals f1, right? So it is in the 0 by 0 form. So we can apply L'Hopital rule here. Yes. So straightforward. Applying the L'Hopital rule, we have f1 g dash x minus f dash x g1, and denominator we have g dash x minus f dash x, right? Now if we simplify this, limit x tends to 1, we have, now observe that no condition has been given about g dash 1 and f dash 1. So we can safely assume that these are not equal. So assuming these two values are not equal, let me see what is happening. we have g dash 1 f1 minus f dash 1 g1. Yes. Now we know f1 and g1 are equal to, so it is 2 g dash 1 2 f dash 1 by g dash 1 minus f dash 1. So basically it is getting cancelled out, right? G dash 1 minus f dash 1. Only one thing is that we have assumed here that g dash 1 is not equal f dash 1. Okay, we have assumed this. So the answer is 2 because this thing will get cancelled out. So the answer is C. Yes.